Lecture 14, Unit 3. This is the multiplication rule of conditional probability. My name is Jorge. And so the objectives for this lesson is that we're going to go ahead and talk about compound events and find the probability of compound events. And then we're going to use the multiplication rules. We're also going to talk about conditional probability of an event. So the first thing is that the multiplication rules can be used to find the probability of two or more events that occur in a sequence. So for example, if I toss a coin and roll a die, so I can find the probability of getting head on the coin and then a 4 on the die. Now these two events are said to be independent since the outcome of the first event, tossing a coin, does not affect the probability outcome of the second event, which is rolling a die. So again, two events A and B are independent events if the fact that A occurs does not affect the probability of B occurring. So again, for example, rolling a die and getting a 6, then rolling a second die and getting a 3. Now, the multiplication rule says that when two events are independent and the probability of both occurring is the probability of A and B, which is equal to the probability of A times the probability of B. So here's an example. Coin is flipped, die is rolled. Find the probability of getting head on the coin and a 4 on the die. So the probability of H and 4 is the probability of H times the probability of 4, which is 1/12. So here we have an example. An urn contains 3 red marbles, 2 blue, and 5 white marbles. A marble is selected and its color noted. Then it's replaced. Second marble is selected and its color noted. Find the probability of each of these. So first thing is with selecting 2 blue marbles. So here the probability of B and B is 1/16. The next one is 1 blue marble and then, 1 white marble. So here you can see that the probability of B and W is 5/32. And then the last one is 1 red marble and 1 blue marble. So the probability of R and B is 3/32. The next example is a survey on stress. A Harris poll found that 46% of Americans say they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say that they suffer great stress at least once a week. So since they're independent of each other, I just multiply the probability of each of the events 3 times, and I get 0.097, so about 10%. Now, in the previous example, the events were independent of one another, since the occurrence of the first event did not change the occurrence or the outcome of the probability of the second event. Now, when the occurrence of the first event, in fact, changes the probability of the second event, then these two events are dependent on each other. So, the example, suppose the card is drawn from a deck and not replaced. Then a second card is drawn. What is the probability of selecting an ace on the first card and a king on the second card? So 4 out of 52 is the first card. Since we're not replacing it, then the sample space is no longer 52, but now it's 51. 4 kings out of 51, so it's approximately 0.006. Okay, when the outcome of the occurrence of the first event affects the outcome of the occurrence of the second event in the way that the probability is changed, then these events are said to be dependent events. So, example, drawing a card from a deck, not replacing it, then drawing a second card. Selecting a ball from an urn, not replacing it, then selecting a second ball. The next thing is conditional probability. Now, the conditional probability of event B in the relationship to event A is the probability that event B occurs after event A has already occurred. So the second multiplication rule states when two events are dependent, then the probability of both occurring, P of A and B, is equal to P of A, the probability of A, times the probability of B given A. Now, so here we have 3 cards from an ordinary deck, and they're not replaced. So find the probability of these 3 events. So the probability of getting 3 jacks. So every time I get a jack, then my sample space reduces and the number of jacks is reduced. Getting an ace, a king, and a queen in that order. Again, you can see that my sample space is reduced, and then getting 3 clubs. So conditional probability of event B in relationship to event A was defined as the probability of event B occurs after event A has already occurred. So the conditional probability of an event can be found by dividing both sides of the equation for multiplication rule 2 by the probability of A. So the probability of A and B is equal to the probability of A times the probability of B given A, or the probability of B given A is equal to the probability of A and B divided by the probability of A. And if you remember, I showed this in class. So the formula for conditional probability and the probability of the second event B occurs given in the first event A has occurred can be found by dividing the probability that both events occurred by the probability of the first event has occurred. So here's an example. A box contains black chips and white chips. A person selects 2 chips without replacement. if the probability of selecting a black chip and a white chip is 15 out of 56, and the probability of selecting a black chip on the first draw is 3/8, find the probability of selecting a white chip on the second draw given that the first chip selected was black. So B is a black chip, W is a white chip. So the probability of W given B is equal to the probability of B and W divided by the probability of B. Probability of B and W is 15 out of 56. Probability of B is 3 out of 8, and we get 5/7. So the probability of selecting a white chip on the second draw, given that the first chip selected was black, is 5/7. Here's another example. So survey of women in the military. A recent survey asked 100 people if they thought that women in the armed forces should be permitted to participate in combat. So the results of the survey are shown. So here's the contingency table. And we've done this, and it makes it a little easier to find these probabilities. So we're going to let M be male, F be female, Y be yes, and capital N be no. So the two that we're going to answer is the respondent answered yes, given that the respondent was female, and the second, the respondent was male, given that the respondent answered no. So the first one is the probability of Y given F. So again, that's the probability of Y and F divided by the probability of F. So 8 over 100 divided by 50 over 100, which is 8 over 50, which is 0.16. And then the second one is the probability of M given N. So the probability of M and N is 18. Well, actually, it ends up being 18 over 60. Now, if you go back to the table, and if you notice, so the probability of M given N. So let's go back to the table here real quick. So the probability of M given N. So here, we look at N. That's going to be our denominator. How many of those are male? 18, and that's how we ended up with 18 over 60. So there's two different ways that you can do that. You can use the formula, or you can have the table, use the table to find the probabilities. So the probability of M given N is 0.3. Now, at least, and we had an example in class of an at least. So here's another example, and hopefully it'll become a little clearer. So game is played by drawing 4 cards from an ordinary deck. Now we're placing each card after it's drawn. Find the probability that at least one ace is drawn. So it's much easier to find the probability that no aces are drawn, then subtract that value from 1 to find the solution. So we have two things. E is going to be at least one ace is drawn, and then not E, or the complement of E, is that no aces are drawn. So first let's find the probability that no aces are drawn. There's 4 aces, so the probability of no aces for the first card is 48 over 52, then 47 over 51, so on. And that gives us 0.72. So it's about 72% chance that no aces are drawn. So what's the probability that at least one ace is drawn? So then we take that information and we subtract it from 1. So the probability that at least one ace is drawn is 0.26. Here's another example. A coin is tossed 5 times. Find the probability of getting at least one tail. So the probability of no tails would be 1 over 32. In other words, that would be all H, right? So H 5 times. So then the probability of at least one tail then would be 1 minus that, which is 1 minus 32, which is about 0.97. So about 97% chance that if you toss a coin 5 times, you'll get at least one tail. Last example, Neckwear Association of America reported that 3% of ties sold in the U.S. are bow ties. If 4 customers who purchased a tie are randomly selected, find the probability that at least one purchase a bow tie. Again, find the probability that you don't get any bow ties, right? So that's going to be 0.97, and then you're going to multiply that 4 times. You get 0.886. Subtract that from 1. So the probability that at least one customer purchased a bow tie is about 12%. And that's the end of Lecture 14, Unit 3. Thank you.